rise in the global temperature in recent times, and depletion of the ozone is one of the major reasons behind it. Today we will discuss the major factors which are responsible for the ozone depletion in Antarctic region. Why it is more prone. The Earth's atmosphere is divided into several layers that appear in a series as follows: Troposphere, Stratosphere, Mesosphere, and Thermosphere, which is further divided into Hydrosphere, Ionosphere, and Exosphere. The ozone layer is present in the stratosphere and plays a significant role because it protects the life on Earth from the harmful ultraviolet rays due to excessive exposure to the sun that can lead to an increased risk of skin cancer and impact the immune system. UVA, it is also called black light, invisible to human eyes. It causes tanning and helps in vitamin D synthesis. UVB, it causes erythema, skin redness, cataracts, and snow blindness. The sunscreen SPF, sun protection factor, in actuality is the ability to protect from UVB. UVC, it is the most dangerous as it damages the DNA and is used in the inactivation of microorganisms by destroying their nucleic acid, thus, known to be germicidal, and is widely used in wastewater treatment. Thus, the ozone layer holds great importance. Tropospheric, or ground-level ozone, is not emitted directly into the air, but is created by chemical reactions between oxides of nitrogen, NOx, and volatile organic compounds, VOC. This happens when pollutants emitted by cars, power plants, industrial boilers, refineries, chemical plants, and other sources chemically react in the presence of sunlight. Ozone is most likely to reach unhealthy levels on hot sunny days in urban environments, but can still reach high levels during colder months. Ozone can also be transported long distances by wind, so even rural areas can experience high ozone levels. In the 1970s, scientists discovered that an ozone layer has slowly been disappearing, and evidence showed that man-made chemicals were responsible for it. Chemicals such as CFCs and nitrogen oxides emanating from a range of industrial and consumer appliances, especially halocarbon refrigerants, propellants, and foam-blowing agents, release chlorofluorocarbons, hydrochlorofluorocarbons, and halogens that are considered to be ozone-depleting substances, ODs. Compounds are emitted from the surface and enter the stratosphere through turbulent mixing, which mixes molecules much faster than they can settle. Through photodissociation, they release halogen atoms, chlorine, bromine, which speeds up the breakdown of the ozone into oxygen. Halocarbon emissions have been observed to deplete the ozone layer. Thomas Midgley Jr., an American chemist in 1928, synthesized a group of non-flammable non-toxic chemicals called chlorofluorocarbons, called CFCs, that were safe to use as coolants in refrigerators, replacing toxic ammonia and methyl chloride that were earlier used as coolants. CFCs are mainly released from solvents or sprays. It is a highly inert compound due to the presence of chlorine and bromine. Thus, it moves through the troposphere and reaches the stratosphere, where the presence of high energy breaks the chlorine bond and releases the atom. It was widespread by the 1970s in refrigerators and air conditioners, of course, but also in deodorants, hair sprays, bug sprays, and paints, styrofoam packaging, and fire extinguishers. This led to a release of about 1 million metric tons of CFCs every year, worth about $1 billion in annual sales. However, CFCs started to create an unrecognized problem high in the stratosphere. CFCs are harmless in the lower atmosphere, but have a long lifespan of 40 to 150 years, as suggested by researchers Frank Sherwood Rowland and Mario Molina in 1974. Over time, the CFC molecules would drift up into the stratosphere, where ultraviolet light would break them down into free chlorine atoms. Upon contact with ozone, these atoms would trigger a chain reaction, causing the ozone layer to thin. The theory quickly gained scientific support. Countries including the US, Canada, Norway, and Sweden banned non-essential aerosols which contained CFCs, but the production of CFCs continued for refrigerants and other uses. However, chemical companies such as DuPont, the largest manufacturer of CFC, denied the link with ozone depletion, saying conclusive evidence had yet to be presented. In 1985, British scientists who had measured total over the interactive since 1957 made an extremely concerning discovery. Compared to 10 years earlier, there was 40% less ozone above the southern hemisphere in September and October. NASA's satellite data soon confirmed that the ozone layer was indeed thinning, with a growing hole over Antarctica. Ozone in the air we breathe can harm our health, especially on hot sunny days when ozone can reach unhealthy levels. People at greatest risk of harm from breathing air containing ozone include people with asthma. Learn more about health effects. Elevated exposures to ozone can affect sensitive vegetation and ecosystems, including forests, parks, wildlife refuges, and wilderness areas. In particular, ozone can harm sensitive vegetation during the growing season. Air quality forecasts are often given with weather forecasts on handheld devices, online or in the paper or television. People most at risk from breathing air containing ozone include people with asthma, children, older adults, and people who are active outdoors, especially outdoor workers. In addition, people with certain genetic characteristics, and people with reduced intake of certain nutrients, such as vitamins C and E, are at greater risk from ozone exposure. Children are at greatest risk from exposure to ozone because their lungs are still developing and they are more likely to be active outdoors when ozone levels are high, which increases their exposure. Children are also more likely than adults to have asthma. Depending on the level of exposure, ozone can cause coughing and sore or scratchy throat, make it more difficult to breathe deeply and vigorously and cause pain when taking a deep breath, inflame and damage the airways, make the lungs more susceptible to infection, aggravate lung diseases such as asthma, emphysema, and chronic bronchitis, increase the frequency of asthma attacks. Some of these effects have been found even in healthy people, but effects can be more serious in people with lung diseases such as asthma. They may lead to increased school absences, medication use, visits to doctors and emergency rooms, and hospital admissions. Long-term exposure to ozone is linked to aggravation of asthma, and is likely to be one of many causes of asthma development. Studies in locations with elevated concentrations also report associations of ozone with deaths from respiratory causes. The pollutants are released in the troposphere. As the sunlight falls on the Earth, the atmosphere heats up and so is the air in the troposphere, making it warm. This warm air starts to move upward or reach the stratosphere. These pollutants, specifically the ozone-depleting substances, are all over the atmosphere, but they have a significant impact in the Antarctica region. The ozone hole is prominent in Antarctica region due to three factors as follows. Temperature: Antarctica lies in the South Pole, which is even colder than the North Pole or the Arctic region. The natural temperature in Antarctica can vary from 10 degrees on the coast to -55 degrees on the inland. It is the coldest place on Earth. Sunlight: normally, the sunlight reacts with the ozone layer and the ozone molecules dissociate into oxygen molecules and release heat. Thus, sunlight participates in limited ozone destruction. O3+ sunlight release heat. But as the layer reduces, the reaction between the sun and the ozone would decrease, which would, in turn, bring down the amount of heat released. This is another reason for reduced temperature levels in Antarctica. Polar vortex: Antarctica has one of the strongest clockwise winds on Earth, which begin blowing in May and June. An enormous ring of moving air forms over the Antarctica continent during winters as these howling stratospheric winds create a cold polar vortex. During winters, the stratosphere over the continent becomes colder than anywhere else on Earth. Due to the spherical shape of the Earth, the speed at which the Earth rotates at its axis is highest at the equator as compared to that at the poles, simply because the wind has to cover a larger distance at equators than the poles in 24 hours. Therefore, the wind from the equator follows a curved path to reach the North and the South Pole to form a polar vortex. Thus, the polar vortex is formed at extremely low temperatures and low air pressure. It occurs in the Northern Hemisphere and the Southern Hemisphere in the Arctic and the Antarctica region respectively. It whirls in an anti-clockwise direction in Arctic and clockwise in the Antarctica region. The temperature inside the vortex drops below -76 degrees Celsius, causing other molecules to condense into icy particles that form the polar stratospheric clouds. Polar stratospheric clouds: at about 60 degrees southern latitude, the polar stratosphere clouds originate at a height between 10 to 25 kilometers only during the winters and the early springs. Based on their particle size and formation temperature, Clouds are classified into Type 1 and Type 2. Type 2 clouds are also called nacreous or mother-of-pearl clouds because they typically range between 10 to 200 kilometers in length and thickness, and are comprised of ice crystals that form when temperatures are below the ice frost point, which is normally below -83 degrees Celsius. These clouds appear colorful as the ice crystals behave as a prism and split the light into colorful components. A central role played by polar stratospheric clouds in the development of the ozone hole in Antarctica is that these clouds are responsible for facilitating heterogeneous chemical reactions. During these reactions, free radicals of chlorine are produced in the stratosphere, which directly destroys ozone molecules. The chlorine reservoir molecules attach to these ice particles that make up the clouds and all through the dark long winters of July and August. More chlorine binds inside the vortex and the polar stratosphere becomes increasingly large. Ozone is one of the 6 common air pollutants identified in the Clean Air Act. EPA calls these criteria air pollutants because their levels in outdoor air need to be limited based on health criteria. There are National Ambient Air Quality Standards, NAQS, for each of the criteria pollutants. These standards apply to the concentration of a pollutant.